SYZ conjecture.
So thank you very much for the introduction. Thank you also to the organizer for the nice conference and the invitation. So the goal of my talk will be to talk about what is now called, I call like a non-Archimedean approach to a conjecture that I will state, which is a conjecture in algebraic differential geometry. So you will see that the starting point may be a bit maybe far from what you usually are working on if you work more like with graph or toric geometry, tropical geometry of matroids. So it will be very algebra geometric. But what I want to advertise is really how a problem, which may be a bit far, actually motivated some of the notions that you may have encountered while maybe studying non-Archimedean or tropical geometry. So you can see this as first like an opportunity to see a very fascinating conjecture in geometry, and also as a motivation for some of the work the community non-Archimedean tropical geometry is doing. So the setting that I will consider for the conjecture is the following. So I will work with families of varieties. So my family is X, and is a family over a curve. You can think of this curve as a smooth affine curves, where I remove maybe, for the moment, I remove 1 point. Like let's say I remove 0. So this is a family. So for any value different from 0, I'm really taking an algebraic variety. I assume my family to be very nice. So these are all smooth, connected. The family is projective. So in particular, I will fix n to be the complex dimension of a smooth fiber. And since I work in the projective setting, I can also fix L an ample divisor, so a polarization of my variety X. Okay. And now I want to make some assumption for the kind of family I'm considering. So the first assumption is that I assume the canonical bundle, so Kx, to be trivial. So what does this mean at the level of the geometry of the fiber that I'm considering? So I write this xt, the fiber over t. So this means that in particular on xt, I'm saying so canonical bundle trivial means that I can find omega t, an over vanishing holomorphic n form. Okay. And once we have an n form, we can actually just by taking omega t wedge omega t bar, standard like operation. I mean, this becomes now an n form. So it means that it becomes a measure on the variety xt. So this is usually called a Calabi-Yau measure. And I can even like fix and normalize it just by dividing by its volume. So these are pieces of data that we get from this assumption. So I assume my family to be globally trivial, and that this in particular implies that all my xt are really Calabi-Yau n-dimensional varieties. But this comes for free, then a very deep result that it also follow from the assumption of the fact that xt is as this nowhere vanishing holomorphic form is an important result by, so we write as Calabi-Yau theorem. Okay. So it was conjectured by Calabi, proved by Yau, and it's a very deep result. So this is now an n form, but what this theorem like guarantees is this actually this n form comes from the wedge product of a 1-1 form. So let me write it precisely. Actually, this n form, for this n form, there exists a unique Kähler form. So I will call this omega CYT. So this is a Kähler form such that, as I say, like if I take its wedge product, I get exactly my mu t. And again, this is normalized. So also on this side, I have to normalize. And in which sense this is unique? So it's unique because if I take the class associated to this 1-1 form, I'm in the class of depolarization. So this is, I mean, may look very unfamiliar. I mean, this is like, if you really see what this equality is asking, behind the scene, there is the solution to a very difficult PDE equation, okay? So I'm not claiming that this is something, I mean, this is very differential geometric, this problem. But I mean, what it's, you will see why I want to emphasize this result, because later we will see that we have a non-Archimedean analog of this result. So it's important to see that already in the complex setting, we can start from what is a measure and actually cook up a form which is associated to a measure via a difficult operator, which in this case involve a PDE. Okay, so I think, I mean, yeah, this was one of a huge result by Yao, the proof that this always exists. So, and it even exists, like, I mean, we can even say something about the regularity of this. It's always like C infinity. Okay, and then maybe let me make a second assumption on my family. Maybe I can write here, or maybe not. Okay, yeah, maybe. So the second assumption that I want to make is similar to what Bernd was saying about maximality. So I also assume that my family X is what is said to be maximally degenerate. Okay. So there are various ways to think of maximally degenerate. So the idea is that here I have an n-dimensional variety, and I want to be able to extend it over 0 in a way that my variety will break into as many pieces as possible. So in this case, the picture is in dimension, let's say n equal to 2. And so I'm saying that I can break into pieces, like suppose maybe like some intersection of hyperplane, such that 3 of them, let's say 1, 2, and 3, intersect in a point. So what's a way to encode this more precisely? So I can think of this degeneration as living over 0, and I can think of its dual complex. So the same of the dual graph as before, like in the previous talk, we were starting from a graph and constructing an arrangement of curves whose dual graph was the graph given. So here in higher dimension, we can do precisely the same. We don't talk about dual graph, we talk about dual complex, because it's not just one-dimensional. But saying that it's maximally degenerate is asking that the dual graph, so the dual complex, so I would denote this dx of a minimal degeneration. So I will now comment on this minimal as maximal dimension. So it's maximally degenerate, so it's as dimension. So here we now talk about as dimension n. Okay, so the fiber has complex dimension n, and I'm asking this dual complex to have real dimension n, which is the maximal one. Quick comment about minimal degeneration. So I have to fix the class of degeneration that I'm allowing. I don't want them to be too singular, otherwise I could just degenerate everything to a point. It would be meaningless, like my dual complex will be just a point. But I also want to fix some minimality in the sense that I don't want to blow up things that are like unnecessary. Otherwise, by blowing up, I can always create some maximally dimension faces. So I fix a right class using some birational geometry like notions, which I will just now call minimal degeneration. And the point is that it does not depend the dimension on the particular minimal degeneration that I choose. Any minimal will give me a well-defined dual complex as homomorphism type. Yes. In this case, yes. Yeah. I mean, it will be the best we know is that it's a pseudo manifold. And that, I mean, gives us also that the dimension is pure, yeah. Yeah, sure. Yeah. Yes, in this case, yeah, it will be simplification. Like it's really like the game, how we construct is really for any components, and here I have 4, I get a vertex. If 2 components intersect, so here I see like they intersect, for instance, any 2 of them intersect along a line, I get an edge. So I get these edges here. And then whenever 3 components intersect, I get a 2-phase. So here they intersect, so I get this 2-dimensional phase. And you can see that any 3 of them intersect. And then, of course, 4 of them do not intersect. So this is really the boundary of a tetrahedron. I don't have a 3-dimensional phase, otherwise this will mean that there is a point where 4 of them intersect. So it's the same recipe of a dual graph, just in higher dimension, and I'm really gluing simplices. Okay. Okay, so now this is the setting where I'm gonna state the conjecture we want to consider. And so you can take this as a motivation for the work I'm gonna talk about. And it's the following. So this is a conjecture. And it says that I want to leave here some space. So for sufficiently small t, the variety xt, for the variety xt, there exists what we call a special Lagrangian torus vibration. I will explain. On an open subset of xt. Okay. I mean, let's analyze this statement slowly. So we are saying that we have a family, and when we are approach 0, we are sufficiently close to 0. Then the expectation, so I will just now draw xt. So I fix t close enough. This is my variety xt. And the expectation is that this variety xt, this Calabi-Yau variety, can be actually fibered. So it emits a vibration over a certain base. And these fibers are, so let's take piece by piece. So first of all is a torus vibration. So I'm asking that most of my fibers are tori. Okay, so if I fix F and F is a fiber, then I'm asking that my F is actually homeomorphic to S1 to the N. So I have an n-dimensional complex variety, and claiming that I can slice this in tori over a n-dimensional real base. But we're asking more, because these are, I mean, this is just if we analyze this at the topological level, then we're saying we have a torus vibration, maybe not everywhere. So we could have some points where correspond to some like maybe singular fibers, like some pinch tori, for instance. But almost everywhere, let's say, we have nice tori. But we want it to be also spatial and Lagrangian. So these are 2 conditions, one which involve the complex structure and one which involve the symplectic structure. And actually, this is what makes the conjecture very hard and basically known only in some cases, because constructing spatial Lagrangian torus vibration is very hard. But you can think of this problem as like, why this conjecture will be, I mean, it's very important, actually inspire like all areas of mathematics, which like goes in the direction of mirror symmetry, because it's really saying that I just assume my canonical line bundle to be trivial, to have a family, and then in the limit of my family, I can always fiber my variety. So this is really a deep conjecture about the structure of the Calabi-Yau geometry. Okay. And I can be even a bit more precise on how big we expect this open subset to be. So, I mean, here there are various versions of the conjecture. The one I want to consider is what I call the metric, SYZ. So SYZ is because this idea was inspired by Strominger, Yao, and Zaslow. And metric because I want to express how big I expect my open subset to be in a metric sense. So I want that if I given a delta sufficiently small, then the open set that I get is so an open set of Calabi-Yau measure 1 minus delta. So it means that I choose delta small enough, then I can find T small enough such that I will have this toric fiber almost everywhere, like on an open whose measure is as small as you want, depending on delta. So it's 1 minus delta. Okay. Now let's see. So as I say, like this was proposed by Strominger, Yau, and Zaslow as trying to explain some phenomenon in mirror symmetry. And then there was like a deep development of different approaches to study that. And the approach we're gonna consider is the approach to use non-Archimedean geometry. So let me write non-Archimedean approach. Okay, so here, I think the starting point is really like some insight of Kontsevich and Soibelman. And so maybe, okay, they could, I mean, I could write many pages of conjecture that they made, but I want to summarize this in just few lines and give you some evidence of why we should think of this. I mean, what are the evidence for this conjecture? So this conjecture, Kontsevich and Soibelman, is a bit like their approach to tackle the SYZ. And the idea is that a key object to look at should really be this dual complex dx that we consider here. And we should view this at the same time as, so this should play the role of the base of the SYZ fibration. So their guess is that at the moment we are not able to construct, but if we should start, our starting point to construct should be, for instance, construct the base and then try to see how we should fill all the fibers over the base. The idea is this base, the role of this base should really be played by this dual complex. And on the other side, we can also think of this dual complex as the metric limit of xt, so the Calabi-Yau fiber with the metric coming from the Calabi-Yau theorem. Okay, so let me try to give you an idea of why we should think of this dual complex in this way. So we think, I mean, and also what has this to do with non-Archimedean geometry? So we saw that this dual complex is a simplicial complex. And actually, we can embed these inside the non-Archimedean space. So this is the non-Archimedean space associated to like of X. So actually, you can think really of XAN as not just a topological space where you can embed this particular dual complex, but is homeomorphic to the limit, like to all the dual complexes, in the sense that I could vary my degeneration. I could do some blow-ups, add new components. This will give me more rich dual complexes. And all of them, I can still embed it inside XAN. Taking the limit, I get the all non-Archimedean space. I mean, for instance, if your variety can be embedded in a toric variety, this is also equal to the limit of all the possible tropicalization. Okay, so you can really think of this as really containing all the dual complexes, so in particular, this one, the one associated to a minimal one. And in which sense, I mean, I want to try to explain why this has to do with a metric limit. So wait, okay, I keep this. This is the all this, and I clean this one. So there are maybe, I think, two results that are quite compelling about the metric limit. So the first one is about a result of measure convergence. So this is due to Buxbaum and Johnson. So they prove the following. So we say that here on xt, we have our omega cyt, a metric, and then we also have the measure mu t. So at the level of measure, I can look at what's the limit of mu t. So I have mu t for any t when t goes to 0. And what they prove is that mu t converges to the Lebesgue measure on d of x. So at the level of measure, not yet of metric, but the level of measure, if I start with the mu t and I approach 0, then what I get is precisely the Lebesgue measure on this dual complex. That's why, measure speaking, we should think of that as the limit. And then the second evidence is what I mentioned before, that we have a non-Archimedean Calabi-Yau theorem due to Buxbaum and Johnson, which says something similar to the Calabi-Yau theorem. So there exists a unique continuous, I will explain the terminology here, metric. Now, this is now not omega Calabi-Yau, it's omega non-Archimedean on now the non-Archimedean space with respect to the polarization L, such that, okay, here I will write like such that, again, a sort of equation involving YAN will give us precisely the analogous of mu t, so the Lebesgue measure on d of x. And the equation that I want to write here is it should be thought as the analog of the PDE equation. The PDE equation is called a Monge-Ampere equation. So here we call the non-Archimedean Monge-Ampere. Sure.
I don't understand what you mean by Lebesgue measure. So what I have in mind is a polyhedral sphere, maybe triangulated sphere of appropriate dimension. There could be many different realizations.
Yeah, but the point is that, okay, homeomorphically, sure, we are working with a sphere, but you really need to think this is a triangulated sphere. You will like, I'm fixing a polyhedral structure. And what is true is that this is a canonical piecewise affine structure. So it means that on each face, I can make sense of Lebesgue measure. And then since it's a integral affine structure, I know that when I change basis, this is just integral affine transformation. And so the Lebesgue measure is preserved. So I can make sense of what means Lebesgue measure on this tetrahedron, since I also have a canonical piecewise affine structure. Yeah. So, okay, so here really the analogy is that we think of, like, we have this complex setting and the non-Archimedean setting. The first result tells us that we should think of this mu t, so this Calabi-Yau normalized measure, as having as analog the Lebesgue measure on this dual complex. And then we saw that we could always find omega c t to the n divided by equal to mu t. And here instead, the analog is that we can always find omega an, which give us the Lebesgue measure on D of X. So these are the two pieces of evidence that whatever happens on D of X should be thought as really what happens on our variety xt with the measure. So on this side, I will now have basically my dual complex, and I want to understand this omega an. This is the analogy, and you can legitimately ask, okay, you're really building like a sort of analogy, but to which extent? So here we have the complex and the non-Archimedean. To which extent these two are connected? Like, okay, maybe we're just reproving results in the non-Archimedean setting using different tools, because even this operator is really constructed very differently from this type of PDE equation, but how the two picture relates. And it's very legitimate, as I say, question, and very interesting that a couple of years ago, we had like a incredible results which connected the two sides, which was like groundbreaking result, which really made this intuition of Kontsevich and Soberman very, very concrete. So let me explain that. I mean, with the result that I'm gonna tell you, you will see really how these two are connected and why we can reduce a problem in complex algebraic geometry to a problem in non-Archimedean and polyhedral geometry, which is, Okay, but to do that, let me just fix. So I say that here we have a metric that is semi-positive. So let me maybe just tell you how I think of this metric, since I want to explain how this metric is gonna enlighten the original setting. So there, let's write it as a remark. If we fix now a model for my family, let's even assume that it's like a nice SNC model. So I'm saying that basically I'm filling my fiber over 0 by adding an SNC divisor. I'm not asking any minimality, just an SNC divisor. So first, you may know that we can actually retract the old Berkovich space onto the dual complex of the special fiber. So I really need to think, okay, I'm filling also over 0. Maybe that's not minimal. Maybe I have many more components, right? I still have a dual complex associated. This embed inside the Berkovich space, but I also have a retraction in the other sense. And second, I fix a model for X, but I also fix a model for L. So meaning that over X, I had my line bundle, and I find a way to also extend the line bundle over 0. So that's what curly L means here. And once we fix curly L, we can actually think of this omega an as being represented just by a function, like a sort of potential for the measure, P naught on xan. So the way I usually think of this metric is just, I imagine that I fix once for all at the beginning one nice degeneration, and then now thinking of the metric means that I'm thinking of like saying that there exists a matrix such that means that there exists, I cannot really construct it, but I know it exists a certain function on xan which solve a particular equation. And just note that saying that my omega an is semi-positive implies what? Like, how do I see semi-positivity at the level of this function? It implies that my phi naught is convex on each face of the dual complex. So we can really think of semi-positivity as a convexity notion. So we are getting towards like translating our problem in more like polyhedral terms. Okay, but what I promise, like how to connect the two sides. And so let me tell you the result that was proved by Yang Li. So I will state first a conjecture, and so that the theorem will be just one line. So the conjecture that I call invariance property. It will be a conjecture just involving non-Archimedean geometry. So he says the following, that we can find, so there exists a degeneration curly X, curly L, a degeneration of my given family XL, such that, so I can just call phi naught the solution to the non-Archimedean Monge pair. So such that phi naught solution to the non-Archimedean Calabi-Yau equation, the one that is still written there, yeah, equation, such that my phi naught, so something about the solution, satisfy the following. So if I take the interior of, so tau for me is a maximal phase. I take its interior of the dual complex. This dual complex sits inside the dual complex of this knot. What am I asking is that on this interior, phi naught is equal to rho of X compose, phi naught compose rho of X. So let's see what this means. So I have my dual complex, the minimal one. So this is D of X. Sits inside maybe a bigger dual complex, okay? But this is not relevant for us. Now I take all the maximal phases of my dual complex. So here, this is an interior of a maximal phase. And what I'm saying is that actually the function, and I know that I can retract my all Berkovich space, my non-Archimedean space here. And what we are claiming is that actually, so there will be points, many that will be retracted there. Actually, the value of the function here is completely determined by the value of the function on the dual complex. So it means that the solution that we are looking at is almost everywhere completely described by just a function on the dual complex, which we know it has to be convex. So it means that the function we are looking for is just like we could try, and that's exactly the goal, to reduce the study, like to believe this conjecture, reduce the study of a problem just on the dual complex. And then if the conjecture holds, then it means that we basically describe the whole function, because we can just pull back by the retraction. And this is exactly what Yang Li exploited. So it's groundbreaking theorem, so this is due to Yang Li, was that if the invariance property holds, then the metric XYZ holds. Okay, which is very, very surprising, because this is a conjecture just in non-Archimedean geometry, while, as I stated, the metric SYZ has nothing to do with non-Archimedean geometry. But what we're saying is that if you can actually produce a function with this property, and we know that this function is the solution to the non-Archimedean. We think of the non-Archimedean as the limit. We can really use that sort of going back to the variety xt and actually construct this torus vibration. Okay. So as you can imagine now, all the focus is in trying to prove this part. And it's not an easy task, because if you read the conjecture, it involves at the same time the choice of a degeneration and being able to say something about this solution. But this solution is highly non-constructive. So, it's not really clear, and it could also be possible that maybe we don't see this property for the solution just because we did not pick the right model to study. What the other question? Yeah. But okay, there is this extra thing that the model also prescribes the retraction. And even if, same skeleton, same subset of the dual complex may be realized as dual complex of different model, and the retraction could be different. So there is this problem, we know that this dual complex, D of X, is well determined. We know what it is, we can characterize that. But which is the right retraction that ensure this type of property? There are many, any minimal degeneration will retract there. But which one is, and we know that there should be some preferred model, because if each model has a retraction in different retraction, and if all of them will satisfy, then you will have invariance with respect to too many directions. So this, will be, a bit strange in general. That it could be that you have areas where your function becomes sort of constant because it's invariant with respect to too many. But it's still unclear what should be the extra requirement for the degeneration, such that first it exists and second it guarantees something like that. Yeah.
What did the statement have on script L?
Sorry?
What depends on script L in the statement?
This part, the retraction. Yeah. And there was another question? No. Okay, so what I want to show you now is a result that we have where we can actually prove the invariance property. And as I say, here there are sort of two different but intertwined problems: the choice of the degeneration and sort of a description of the solution. So in the setting that I'm gonna tell you, the model is there is a very natural model. So if the first problem is more a problem in birational geometry, choice of the model, then we don't have we don't have issue on that side, but it's more interesting what's going on at the level of the measure. And so it's more it's more like a metric. There are more aspects related to the metric that are interesting. So let me write it as results. So here is the family we're gonna consider. So I fix my X to be a family of Calabi-Yau hypersurface. So Z0, Z1, Zn plus 1, plus T, F, n plus 2Z equal to 0. So this is an equation that I see inside Pn plus 1 with homogeneous coordinate Z. By the degree of this equation, I know that this family is a family of Calabi-Yau. The canonical bundle will be trivial. As a polarization L, I can fix, for instance, the restriction of O Pn minus 1. I think we choose n plus 2, just restricted to X. And this is, this is a family you can think of, for instance, over Gm with coordinate T. Okay, and just to be sure that these are all smooth elements, so here, this is a generic homogeneous polynomial of degree n plus 2. Okay, so maybe let's keep a picture for n equal to 2. Maybe I do it on this side. So when n is equal to 2, I'm saying that, so this all lives inside P3, okay? And when t is equal to 0, so let's try to see what type of degeneration we have. It means that my spatial fiber will be just x0, x1, x2, x3 equal to 0, which corresponds really to the 4 toric hyperplanes in P3, okay? And so the dual complex that I can associate to this spatial fiber is exactly the boundary of the tetrahedron that we drew before. Okay, so this is the family, and the degeneration that I can pick is just, so it's curly X. I can just take precisely the same equation, but now I see this equation not only over, also over 0, so over A1 T. And you see now when T is equal to 0, that's exactly what we get, like a nice normal crossing divisor. And this is my, so this is now the spatial fiber, and this is my dual complex. Okay. But I want to be a bit more, I want really to fix an embedding for my dual complex. So you see that this is just a unit n-dimensional simplex. Okay, the boundary of. So it's really like isomorphic to Sn, to the sphere. But I want to see this inside. Okay, I want to, okay, this is, okay, let's give this an example. This is S2. Let's write it here in general. So it's true in general that my dual complex will be the unit, the boundary of the unit and simplex. So here I should write the boundary of the unit. Okay, boundary of n3 simplex, right? So the unit of the n+1 simplex, if I say boundary, which is Sn. Okay, so in general, this is Sn. I want to see this inside Rn+1. Now, how do I think of this Rn+1? I see this as the real co-character lattice of which toric variety? The one I'm embedded in. So this n is the co-character lattice of Pn+1. Okay, so in this case, I'm inside R3. And this n, the toric variety, this is underlining, this is the co-character lattice of P3. Okay, and what's the advantage of thinking of this dual complex as embedded there? That in toric geometry, we have a very natural duality. So if I have my NR, I also have MR. And we have a nice pairing here, so I can make sense of what is, so let me just, for convenience, write this delta. I can talk about delta check, which is the dual polytope of delta, and lives inside here. So at the level of this example, it means that I have my delta here, and I will also have a delta check also inside R3, which in this case is actually not isometric, but isomorphic still to like a boundary of a unit simplex. Okay. And what's the, I mean, what do we also gain from there is that now I can really fix, so how do I fix the embedding here inside the NR? So I can really think that I'm placing my vertices at the primitive generators of the fan. So the fan of P3 has 4 rays, 1, 2, 3, and 4. And I'm really thinking that a vertex here, let's say VI, I know that this comes from a component DI of my spatial fiber. So this comes from Zi equal T equals 0. But I can actually really make this correspond to Ni primitive generator of the ray Di, so Zi equal to 0 inside P3. Okay, so this is the way I'm really fixing the embedding inside this real vector space that comes from the lattice. Okay, so this is the setting, and I'm gonna write here now. So we have everything now to state the main theorem. So the first theorem, this was with Ulrich, Johnson, McCready, and myself, says the following. So our goal is really, we want to try to get as close as possible to this P naught. So we really want to think of function on the dual complex, which give rise to some measures. And the measure we always have in mind is really the Lebesgue measure. So we want to think of function which give us measure. So what we prove is that for any measure that we can think on the dual complex, so these are symmetric measure on this dual complex delta. By symmetric, I mean that once I fix this embedding here, I can now, so I have my vertices, I can see the action of the symmetric group with n+2 elements. And how this symmetric group is acting by permuting my vertices. So of course, it preserves the dual complex by moving the vertices. And so I'm asking, when I say symmetric measure, I'm asking measures which are invariant with respect to this permutation. So for instance, one example of a symmetric measure, the one we are the most interested in, will be the Lebesgue measure. Like, if I just take an open and measure its Lebesgue measure, and if I move it by symmetry, the measure will not change. So what we prove is that any symmetric measure actually comes from a function on the dual complex. So this QC is the set of functions on the dual complex with real values, so continuous symmetric functions, such that, so these are particular type of functions. So first of all, this function phi extends, they're not just defined on delta, extend to the O and R. And second, they also satisfy a growth condition. So I can write it precisely. If I take phi minus the sup of L, where L are all the elements in the dual lattice. So all the elements in dual lattice, I can think as function on NR, so in particular on delta. This is bounded. Okay, so this is a set. We have a surjectivity, so it means that for any of this type of measure, I can actually produce a function, and I can even say that this is unique if I quotient by the constant function. So I can really say that I have now bijection between these two sets. Okay, so how do we use this result? So we start from we know with which measure we are starting with. We want to solve a problem with respect to the Lebesgue measure, and we want to produce a function that we believe this conjecture should just be a function on the dual complex. So this theorem tells us that, yes, there exists a function, which is also very nice in the sense that it's a function that will actually, it extends, sorry, I forgot something, it extends to and 0. And we know that this function needs to have some convexity condition, otherwise it will not be eligible to be the one associated to the non-Archimedean. So it extends to phi and tilde. So let me call phi tilde the extension. And the other thing that we know is that this phi tilde is convex. Sorry? Yes, so this theorem is in this setting. So good question. So for x as above, we can prove this. Yeah. But okay, the theorem is slightly more general than the way we are going to apply, because we can apply also to other symmetric measures, which are not the Lebesgue measure. For instance, you can even take sum of Dirac masses, as long as you choose your point to be symmetric, like invariant with respect, and this will still produce, tells you that actually that measure is associated to such a function. So we think of this really as, again, a Monge-Ampère operator, because it takes function and gives us measure, and it's sort of like, so I think in the paper we call it really like a tropical Monge-Ampère operator, in the sense that it's really like constructing out of polyhedral geometry by trying to mimic what should happen on each in maximal phase, but then it's global, in the sense that it's really by union of these polyhedral like pieces of Rn that we actually get a full operator on the all dual complex, even if this dual complex is highly non-convex. Okay, and now let me tell you the second result that one can prove. Okay, now maybe this needs like a remark first. Okay, here. So this is, okay, we're just saying that we have a new way to describe. So in the dual complex, we know, starting from the Lebesgue measure, how to produce a function. But actually, this is the important remark, is that if you apply theorem 1, apply to the measure Lebesgue on delta, we get this function phi. So the function, the solution like phi, such that Monge-Ampère tropical of phi is equal to the Lebesgue, give us a new characterization of the solution of phi 0 solution now, the non-Archimedean one, with respect to the same measure. So actually, out of this phi, and in particular out of this phi tilde, we can actually construct a function on the all non-Archimedean space and see that this is actually the solution. So we get really like almost our ends on the solution. And so we can then, just by the way it is being constructed, the fact that this phi induces the solution, we can check the invariance property. And so once we have the invariance property still written here, we have the metric SYZ. So putting everything together, theorem 1 plus the theorem of Yang-Lee produces, verifies the metric SYZ conjecture for this type of family X. So these Calabi-Yau hypersurfaces inside Pn plus 1. And you can wonder, okay, what's special of Pn plus 1? So here we use the duality of toric geometry. Actually, this can be slightly extended in the sense that it's possible to replace Pn plus 1 by some other toric Fano manifolds, but not that many. Like there's been 2 results, one by Yang-Lee itself, which used the same type of strategy, and one by 2 of my co-authors, but they really show that you need to really impose condition on the type of fun you allowed. So, I mean, at the moment, I mean, there are no, it can be extended, but just slightly. For instance, P1 to n plus 1, this also works. Like instead of having a tetrahedron, you will get a cube, and you can sort of use the same type of techniques. But maybe in the last minutes, let me just, where should I write? I keep the theorem here. Okay. So in some sense, if our original goal was to prove the metric SYZ, we're sort of done here for this case of Calabi-Yau hypersurfaces, because we really show that we can prove this property, hence the metric. Hence the metric SYZ exists. But really, the whole heuristic is that the more we know on this side, so the more we know on the dual complex and the metric or its potential, the more really like we can say about this SYZ fibration. That's exactly what Yang Li exploited. So for instance, in this case, we can wonder like, what can we say about the regularity of our solution? Or what can we say actually about this metric? Like we say that, okay, we get this function, but what type of metric does it produce on the tetrahedron, for instance? And so we try to investigate a bit this direction, still in this example where we can, we have this theorem. And here is what we proved. So this is the second theorem. So for theorem 2, so we have this delta that we saw, it's just our Sn that we think of as really like the polytope generated by, induced by the generator of the fan. Inside here, we can fix a regular locus. So how is this regular locus described? So it's the union for all the maximal faces of the interior. It means that if this is my dual complex, I'm taking all the interior, I missed the color. I'm taking all the interior here for all the faces. But I'm taking a bit more. Then I'm also, for all the vertices, I'm taking the star of the vertices in the first subdivision. So what's the recipe? So I fix a vertex V. I do the first barycentric subdivision. So this means that I'm doing this type of subdivision. And now I take in the star. So all the open faces, which contains in their closure the point. So it means that I'm taking also here. So what's left? Like what is delta minus delta reg in this case? So if this is my dual complex, what I'm missing is just in this case in n equal to a trivalent graph. These are the only things that interior, no, sorry, less than that, sorry. It's just these points here. So it's always, if this is dimension n, then this is codimension. So the difference is codimension at least 2. Okay. Okay, so we have this delta reg, and that's exactly on this type of opens, so the maximal face or next to the vertices, where we can really say something about the solution. Like, and it is, okay. So we say two things, theorem. The first thing, we say that the solution, so on delta reg, I fix, so let phi such that tropical non-Jampere of phi gives me the Lebesgue measure on delta. then phi on this is C infinity and strictly convex. Why is this important? Because if my function is strictly convex, means that in particular I can really think of that as a metric d phi associated metric. So it's really like a Riemannian metric associated to phi on delta reg. And so what you can wonder is like, okay, on one side I have my dual complex, I have my d reg, and I could just think of this d reg as just with the usual Euclidean topology, right? The distance coming from the Euclidean topology. On the other side, I have this unknown, but very relevant in our context measure coming from phi, which we know as all these consequences, that if you get your hands on phi, blah, 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 you have something related to the metric SYZ. And now I can try to take the completion. So on this side, the completion of d reg, we all know what it is. It's really like this sphere Sn with the usual Euclidean distance. On this other side, okay, I take a completion. I don't know what it is. How do I relate these two? We know that we have a order continuous surjective map. So the dream will be prove that this is actually an isomorphism, because this will really tell us, first it will match all the expectation we have on the base, or like on this type of measure, and it will really give us a very concrete description on this metric limit. It will tell us that in this case, the metric limit is just the usual, I mean, we just get the sphere with the usual distance, the Euclidean one. But at the moment, that's the best we can prove. So we know that at least it's not too far, but yeah. So, okay, I thank you all for your attention. And if you have questions, I'm happy to answer.